Hello again. In this video, we're going to explore the tangent line problem, and we are building on a context that I introduced in my last video called an overview of calculus. So please do check that out before embarking on this video if you haven't done so already. So let's get started. So let's recap the problem from the other video. You leave your house by car to visit family. 4 hours later, you arrive at your destination, a distance of 200 miles away. And if you recall, I proposed this distance time graph as being slightly more realistic than a straight line segment. So in this one, you start out your driveway at a relatively low speed, and you speed up, and you speed up, and keep speeding up. So not entirely realistic, as you don't slow down or stop for any traffic lights or pedestrians, but more realistic in the sense that it's a smooth curve. And we asked ourselves, what is the speed of the car? How can we calculate the speed of a car at any particular point? So say we wanted to find the speed of the car at t equals 3 hours. Well, you could argue that if you look down at your speedometer, it could tell you that, but that would ruin all my fun. So instead, we realize that we have to find the slope of the tangent line at that point. Only at one point, and that is the problem, because heretofore, in all our previous math courses, the only way to find the slope of a line is using 2 points, and suddenly we're faced with a situation where we have to find the slope using only 1 point. And that's where calculus steps in to help us answer this question. So, since we don't know how to find the slope of a line at 1 point just yet, we're going to use a workaround and find the slope of the line connecting the 2 points, the points that are at t equals 3 and t equals 3.5. In other words, the slope of the secant line. So here's the point that corresponds where t equals 3, and here's the point that corresponds to t equals 3.5. Now we could, to find the slope, it's change in y over change in x, so we could estimate the y values. The y value at t equals 3 looks like it's 110, and the y value for t equals 3.5, well, I mean, I'm sort of approximating, so I don't actually know how accurate I would be, even if I said that this was 150, I'm not sure. So what would help improve our calculations? An equation. So here's the equation of this graph. D equals 12.5 t squared. Your distance from home is 12.5 times the square of the time. And now let's put this into the slope formula. So y2, so in other words, the second y coordinate, we would get by just taking our equation and plugging in the corresponding time. And then where we thought that the y value was 110, we would just do 12.5 times 3 squared to get that y coordinate exactly. And change in x is 3.5 minus 3, that's the run. And if you do that calculation, you get 81.25 miles per hour. So that's your average speed over that interval. You are clearly speeding. So here's our graph again. And we just found the slope of the secant line in the slide before, and this slope corresponds to the average speed of the car over that time interval. So that actually looks like a good estimate of the slope of the tangent line. Let's get that tangent line. So the slope of the tangent line at t equals 3, which of course would correspond to the instantaneous speed of the car, which is what we would like to find. So let's improve our estimate of the instantaneous speed by finding the average speed of the car over smaller and smaller time intervals. So I picked the time interval 3 to 3.5 before. That was sort of arbitrary. Why not make it a smaller interval? So in this table, you see that the average speed we just calculated was 81.25 miles per hour from 3 to 3.5 hours. And we are going to improve this estimate by making smaller and smaller time intervals. So I'm just going to call up that formula, the slope formula, which also obviously gives us the average speed. And you will see that, for example, if we want to go from the time interval 3 to 3.1, we would put 3.1 into this position and here, and we'd calculate that, and you can do that on a calculator if you'd like to check, and it would come out to 76.25. And then from 3 to 3.01, again, so when we put 3.01 in here, 3.01 in here, if you think about it, 3.01 minus 3, that's a time interval of 0.01. And the difference in these two calculations really just tell you the distance traveled by the car in that time frame. And if we work that out, it comes to 75.125. And we repeat. So if you continue doing that, we would get 75.013, 75.001. Now, you might be inclined to think, well, why not just plug 3 in and be done with it? But if you notice, if you plug 3 in here and here, you'd actually get 0 on the denominator and 0 on the numerator, and you'd get an error in your calculator if you tried to do that. So that's obviously we have to have two separate points. We can't just use the same point twice. But if you look closely, we can deduce something from this table, because as the time interval decreases, or as the second time gets closer and closer to 3, we notice a distinct pattern in the average speed. It seems to be approaching 75 miles per hour. So that's kind of an educated guess based on the pattern that we are observing. But being mathematicians, we would like to not just rest solely on what's observable, but also be able to kind of prove things mathematically or algebraically, and that's what we'll seek to do next. So let's introduce a little algebra to help generalize the calculations we were working out in the previous slide. So here's the general formula for the average speed of the car over the time interval 3 to some time t, general time t. And bring that table up, and we noticed from the table that as the second time value got closer and closer to 3, it appeared like the average speed was approaching a fixed value, seems to be 75. And so we are hypothesizing, so the instantaneous speed, we're hypothesizing that's 75, and we know that the instantaneous speed corresponds to the slope of the tangent line. So what do we need to do to this formula to kind of get at that answer more accurately? And that's where we introduce the concept of a limit, which is the basic building block of calculus. So we take that expression for the average speed and we pop this in front of it, and that reads the limit of this expression as time goes to 3, as t approaches 3. And for now, you're going to just have to trust that the answer is 75 miles an hour. But in the next unit, we will learn to actually calculate these algebraically and appreciate why limits are so important in helping build the subject of calculus. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.